Precalculus, this is question number 7 from the chapter 5 review. It says solve the following exponential equations. We're just going to be using, excuse me, so part A, 4 to the x minus 2 equals 8 to the x plus 1. This would be one where you want to express it in the same base. So we're going to write it as 2 squared equals 2 cubed plus 1. A power raised to a power means you multiply the exponents, so you get 2 to the 2 times x minus 2 equals 2 to the 3 times x plus 1. A to the x equals a to the y would imply that x is equals y, right? So if two numbers are raised to a certain power, make them equal, then the powers have to be equal. If it's the same number raised to two powers. So we get 2x minus 4 equals 3x plus 3. And so I get x equals negative 7. Okay. And these can all be checked. Let's try it. 4 raised to the negative 7 minus 2. And just so it comes out to 0, I could even say here, I could just subtract the other side, 8 raised to the negative 7 plus 1. And I should get 0. Okay, perfect. Let's keep going. 3 to the x, 27 to the x minus 4 equals 1000. Seems like a common base of 3 would be a good idea on this side. So that leaves us with 3 to the x times 3 to 3x minus 4 equals 1000. Now we have two terms being multiplied with the same base, so we can add their exponents. So it becomes x plus, I'm going to distribute 3x minus 12 equals 1000. And now, okay, let's go 3 to the 4x minus 12 equals 1000. I'm going to log loop it, apply the definition of a log. Log base 3 of 1000. Okay, we'll go to a calculator for that, but for our final steps we need to add a 12 to that. So 12 plus log base 3 of 1000. And to get rid of the 4, we're going to divide both sides by 4. So here we're going to say 12 plus log base 3 of 1000. We're going to close parentheses and divide by 4. And for right now, I'm just going to store that to a for just a second, so I have that value stored, because when I go back to check for it, so that's my x, I'm going to say 3 to the a times, 3 raised to the a, instead of having to type that out, times 27 raised to the a minus 4. And I'm going to subtract 1000 and see if it's equal to 1000. Okay, alright, let's see if it's equal to 0. Perfect. So the value comes out to approximately 4.572. Okay, we're going to keep going. 3 to the 2x plus 3 over 5x, 5 to the x equals 81. So what's interesting here is we have two different bases, and so that's going to be interesting to deal with. But there are some common bases in that if I would start by writing this as 2x plus 3 over 81 equals 5 to the x. So I'm going to cross multiply both of those back and forth. And in fact, the 81 I'm going to write as 3 to the 4, because it's 9 squared and 9 is 3 squared, so 3 to the 4 should give me this. Which means if two things are being divided which have the same base, I should be able to subtract the exponents. So 2x plus 3 minus 4 equals 5 to the x. I get 3 to the 2x minus 1 equals 5 to the x. Here I can take the log of both sides. You could take it to any base to try and get rid of any one, but in this case, I'm just going to take it a common log on both sides, fly the exponents in front, so I get 2x minus 1 log base 10 3 equals x times log 5. Continuing here, we want to bring the x's to one side, so I'm going to distribute here to get 2x log 3 minus log 3 equals x log 5. Bring over the x log 5 and group like terms, basically. Remember, anytime you see log 3, log 5, those are just numbers. But instead of having to plug into my calculator, I want to see if I can leave it an exact value for as long as possible. And my unlike terms, or like terms that are just constants, I'm moving to the other side. From the left, I can factor out x, and I've got 2 log 3 minus log 3. Oh, I'm sorry, I made an error here where that should have been a log 5. This is a log 5. You got to be careful there. And I moved the log 3 to the other side. So this is also a log 5. I have log 3 to the other side. And now to get the x by itself, this means I have log 3 on this side divided by 2 log 3 minus log 5. Okay, I'm going to do the same and go to the calculator here. We have log 3 divided by, open parentheses, 2 log 3 minus log 5, close parentheses. So it's approximately 1.86. To check it, I'm going to store that again. I'm going to just rewrite the value. I had a, go back to the original, and I'm going to say 3 raised to the 2a plus 3 divided by, oh, it's an interesting format. Okay, 3 to the 4. Oh, I could go a little further. Divided by 5 to the a. And let's see if that, 5 raised to the a should equal 81. Okay, seems like it works. Let's keep going. But let's just note down the value we got. It's approximately 1.869. Okay, continuing here to part D. Saying 9 to the x equals 3 to the x plus 1 plus 4. So here, it's a common base of 3, but there's going to be, this seems to fit the pattern of something else that you may see often. Right, it is 3 squared to the x. I'm going to bring this over to this side, 3 to the, okay, so let's bring it over to the other side. 3 to the x plus 1. I'm also going to bring the 4 to the other side. Now here I'm going to switch position, and because they're being multiplied, 2x, that's commutative as well, so it's x times 2 as well. But I'm going to put the x on the inside, square on the outside. Here I'm going to write it as 3 to the x times 3 minus 4 equals 0. I'll take one other step and write it like this with the 3 in front of that, only to be able to say that this is actually a quadratic in 3 to the x. So if I say let u equal 3 to the x, then I've gotten u squared minus 3u minus 4 equals 0. Factoring this, I get u plus 1 and u minus 4 equals 0. I just want to check that that's okay. So u can take on two values, negative 1 or u equals 4. But we were never solving for u in this, so when we back substitute, I'm going to write it as 3 to the x equals negative 1 and 3 to the x equals 4. So here I have x equals log base 3 of negative 1 and x equals log base 3 of 4. Now this is undefined because I can't take the log of a negative number. If you remember, the graph of a log exists only in the first and fourth quadrants, right? So my answer should be log base 3 of 4. And so it's approximately 1.262. I'm going to store that for the time being as a, and then go back and try and check it in the original equation. And I might put all of them to the same side, so I can do it in one go. 9 to the a minus 3 to the a, 3 raised to the a plus 1 minus 4. And that should equal 0. Ooh, so it didn't come out to 0 because the calculator's doing it numerically, right? Even with 9 decimal places, or however many, 9s. That is basically telling you it's 0, right? Because it's negative 1 times 10 to the negative 12. So 0.0011 zeros, 1. So feeling fairly confident, but just to put in the numerical approximation of that, it's 1.262, right? Hope that helps.